Hello, so today we are talking about QuickSelect algorithm. So QuickSelect is kind of similar to QuickSort, but it accomplishes a different thing. So it helps find the kth smallest element in an ordered list. It can also help you find the kth largest or whatever criteria you want to apply by just changing what you are using, the function you are using, but essentially it's the comparison function you are using. But the standard problem it solves is finding the kth smallest element in an unsorted array or list. I have a video on QuickSort. You can take a look at that to really understand the partition subroutine that QuickSelect uses. But let's just go through the intuition, some kind of an intuition that explains QuickSelect. And so here I'm going to just use this example that I found that uses this sort of like a game or something that you can think of and helps you understand it. So let's say we have a gymnasium that contains 200 children, and you want to find the 1980th shortest child. So this is kind of the children's height is kind of what we are, our array here, and we want to find the 19th smallest height, and so the 19th shortest child, right? So we kind of want to find the 19th smallest element in an array, if that array was the height of these children. So it's kind of kth smallest with k equal to 98. So one thing that you could do is just line all children up from shortest to tallest, but to do that will take forever, right? Because you have to look at them and find the shortest one, put it somewhere, and then find the next shortest one and put it next to the other one, and keep doing this for a long time, right? So how can you speed this up? This is where QuickSelect comes in. And so how does it work? You walk into this number of children and you close your eyes and you move your finger randomly, and then you open your eyes and you are pointing your finger at one of the children. And so let's say you are pointing your finger at Peter, right? And you say, okay, everybody that is shorter than Peter should stand over here, like to some side, and then everybody that is taller than Peter go and stand on the other side, right? So you would have those shorter than Peter on one side, you have Peter, and then you have those taller than Peter on the right side, right? And so this operation here of saying those smaller than Peter, shorter than Peter should go to the left of Peter, and then those taller should go to the right, that's the partition function. That's what the partition does. So we select our pivot, which is Peter. You can see here we selected this randomly. That's a valid QuickSort pivot selection, is by selecting randomly and then doing this step where we move those shorter to the left of Peter and those taller to the right. That's the partition step. So the children do as we said, and he line up those shorter to the left, those taller or equal to Peter to the right, and Peter in the middle. So now we have two groups, and then you count those in the shorter section, and you find that you have 120 children in that section, and then you count those 79, those taller than Peter, and you find that you have 79 children like that. So you have 120 shorter, 79. So you know for sure that the 19th shortest is for sure in the shortest section in this 120 group, right? Because it's smaller, because 98 is smaller than 120, and we know that all the 120 are shorter than Peter. If we go to the right, we will find only those that are taller than Peter, so only in the rank it's 121 shorter or more, right? So there is no need to examine that group at all. So you examine only, now you can just examine this 120 shorter than Peter, right? And you tell the other 79 children that were taller than Peter to just go sit in the bleacher. You don't need to check among them anymore. So you just leave them alone. And then you close your eyes again and do the same procedure again. And you point your finger randomly and you open your eyes. And now let's say randomly you are pointing at Peter's sister. Let's call her Paula, yeah, right? And then you do the same thing. You say, those shorter than Paula, please stand on the left over here. Those taller than Paula, please stand on the right, right? And now they do as you said. So we did the selection of the pivot Paula, and then we did the partition step here to tell them those shorter than Paula to go to the left, those taller to go to the right. And now we have two groups again, right? You count those on the left, shorter than Paula, and you find you have 59 of them. And those taller than Paula, you have 16 of them, right? And you are looking for the 98th. So you have the 59s to the left. That's smaller than 98th. Certainly the shortest one I'm looking for, the shortest 98th I'm looking for is not among them because they are 59. So I know that for certain the 98th shortest is in the 16 children taller group, right? And Paula she's not it either because that's her shortest, her height rank is 60, right? And so because there are 59 shorter than her on the left, right? And so I tell those shorter than Paula and Paula to sit on the bleacher. I don't need bleachers. I don't need to look at them and to examine their height anymore. And so I just leave them alone. And now I go look at the 16th taller, the Paula. But right now, since I'm looking for the 98th, and I know that there are only 59 children, that there are 59 plus Paula, so 16 children already shorter than this 16 group. So I know to find my 98th, I just need to look in the new group. I need to look at the 98 minus 60. So I need to look at 98 minus 60. So I need to look at 38th. Find the 38th one, or the 37 actually, because counting Paula, I need to find 37. And so I go again and do the same thing now on the taller group. So you can see before I went to the shorter group, so the left side only, and now I go to the right side, the taller group only. And so I do the same procedure again, close my eyes, choose randomly, and now I'm pointing at, let's say, Prudence, right? And then I say, okay, those shorter than Prudence stand on the left, those taller stand on the right. And then they do as I said, and now they are standing in two groups. And then I count, I find that there are 37 shorter and 22 tall in the taller group, right? And I'm looking at I want to find the 38th, right? From here I want to find the 38th because I already discarded 16 shorter than my group. And so I just need to find the 38th in the new group, right? And so I find that there are 37 children in the shorter group and 22 children in the taller group, right? And I know that Paula and 59 other children are shorter than my current group, and so I just need to find the 38th, right? So I know that the left side is 37, so my 38 is Prudence, right? And so I know that by now 37 plus 60 are, which are 97, are shorter than Prudence. So I know that Prudence is the 98th shortest child, and I found him. And so that's the check where I found that my k is equal to the pivot index, and I returned that value. And that's pretty much it. That's exactly what QuickSelect does on an array, and this is the intuition that you can understand it with. So let's look at the pseudocode for this. So here we are going to apply the same intuition that we had here. So we want to select in a list, and we are given the boundaries, and we want to select the kth smallest. K, of course, has to be between left and right to be able to find it. So the base case is that if left is equal to right, then that means there is only one element in the list, and so I can just return that, because if you say, like, find me the fourth shortest, smallest element in an array of just one, then I can just return one because there is no other answer. Now, selecting the pivot, here we can do whatever we want. We can select the pivot as the first element, we can select it as the last element, we can select it as the middle, or we can do as the intuition here and select it randomly. Just select a random number between left and right. using, for example, this. That's a valid solution. And once we select the pivot index, now I partition using that pivot index. So I do the fact where I take all those smaller that go to the left and all those bigger go to the right. I do that procedure here. And then now I have a partition list where all those smaller to the pivot are on the left, or those bigger are on the right. And so I check if k is equal to the pivot index. That's the case that we had here with Prudence, right? Where he is the, I know that there are 97 children shorter than him. And so I'm now checking for 38th. I'm now checking for the 38th in this section because I know there are already 16 shorter than him. And so his index, Prudence index is exactly k, right? So I know he's the answer, so I just return the value, right? So that's this case where, let's say I choose the pivot. Let's say I'm looking for the 5th smallest element, and my pivot index was 5, right? So I partitioned. I know all those smaller than that index 5 are on the left, and those bigger are on the right. So I certainly now know that regardless of the order of the left side, I know those are all the elements smaller than it, and my element is still at the 5th index, and so I can just return its value because that's the 5th smallest element. Now, if k is less than the pivot index, right? So let's say my pivot index is 5, and then I'm looking for 3. So I know I don't need to look at the right section because I know that the right section is all bigger than the pivot index. So I just need to look at the left. That's what I did here when I found that 120 children in the shorter group and 79 in the taller group, then I knew that 98 is in the left side, and so I went and looked at the left section, and so that's what we do here. We go look at the left section, so from left to the pivot index -1. Since it's not less or equal, I know that it's not pivot index, so I pass as the right position is pivot index -1. And I'm still looking at the k. That didn't change because I don't know any information about any extra information about the left side. But if k is bigger than the pivot index, so I know for sure with this that if, let's say, k is 6 and my pivot index is, or k is 7 and my pivot index is 5, there is no need to look at the left side. I can just look at the right side and find my smallest element there. But since I know that there are already 5 smaller than my right section, then I don't need to look at the 7th. I can just look at 7 minus 5. So I need to just look at the second smallest in this right section, which is what we did here. So here basically, when I found that I'm looking for the 98th, and I have 16 children on the left, so I don't need to look at the left side. And so in this right section, I want to find just the 38th shortest child, because I already know that there are 60 that are smaller, that are shorter, right? So this is what this does, right? And so this is essentially the QuickSelect algorithm. And you can see here that in quicksort we did call the 2 recursive functions at the same time. So if I go to quicksort here, you can see that we did the calls for the left side and then we recursed on the right side both. But for QuickSelect, we don't need to do that. We can just we completely discard one side and only recurse on one other side, right? And so that will help us. So that definitely means that the performance and the time complexity is better. So let's look at the time complexity. So the good average performance is, of course, for anything involving selecting a pivot and a partition, depends on is sensitive to the pivot choice, right? So for certain choices of pivots, if they encounter certain types of arrays, the performance degrades. So, for example, if we take good pivots that allow us to constantly decrease the search space that we need to select in, by half, like here. So if we choose a pivot good enough that every time we go only to the half of the list, or approximately the half, then we get a, or at least even 1/3, that would be good. Then we get a better solution. Then we get a better performance, right? So let's just look at why is that. So let's say if I'm able to have a pivot that approximately divides the search space into half, or almost half, then that means that the first round I will do select on the entire array, right? So that's n. The second round I would divide almost by half, so I would do n divided by 2. The second step I would do n divided by 2 divided by 2, because I'm also dividing that half by half, and I'll keep getting that 1 divided by 8 until I have only one element in the list, right? And then I will return. And so it's n plus this plus that, so it's the sum of all of this, which is just n multiplied by 1 plus 1/2 plus 4th. And this basically here is a series that converges to 1, right? And so this is n multiplied by 1 plus 1, so it's approximately 2n, so it's O(n) performance. So basically here I'm taking the half just for convenience, but there are some rigorous proof of this, but this gives you the intuition of why it's O(n). Of course, it's not half all the time, but anything that gets around to half, then that's a good pivot choice. So you can see here in a good average case or best case, it's O(n). But if we choose a bad pivot, say for example we choose a pivot that, let's say we choose the biggest element in a sorted array, right? So every time we'll recurse only on the left side, and our new search will get only one element less, and so every time we'll get n, n minus 1, n minus 2, n minus 3. So in that case, we'll end up doing having O(n) squared solution, because we reduce the search space by only 1 every time. And so this is why in the worst case, QuickSelect, just like QuickSort, takes O(n) squared time. And yeah, so that's for QuickSelect. I hope it was useful, and thanks for watching. See you next time. Bye.